Class, is it audible now? Sara, Siddhika, Harsha. It's audible?
Yes, ma'am.
All right. See, in the last class, we had started with hydrostatics. Now, see, before Pascal's law, we had completed. So some of you were not there in the last class. Let me just quickly brief you with the topics which we have completed. So Harsha was already there in all the classes, so she knows. Rest of you, some of you were there, some of you weren't. Hydrostatics, we are currently doing this lesson, mechanical properties of fluids. We are doing this in two parts. We have hydrostatics portion also. We have hydrodynamics also. So in hydrostatics, for us, the fluids remain at rest. The fluids do not move. The fluids remain at rest. All right. So we'll be studying about hydrodynamics also separately. See, we have a separate topic about hydrodynamics also. This lesson is a bit lengthy among all the lessons. Last lesson was very small. We have already completed with mechanical properties of solids. So the first term that we discussed was the concept of pressure. Pressure was what? Pressure of a liquid was basically the total force that is being exerted in the perpendicular direction per unit area. That was pressure, and based upon the formula P is inversely proportional to A, we had certain conclusions. Then atmospheric pressure, which I've already mentioned, that it is 1.01 into 10 to the power 5 pascals, which while calculation, this is sufficient to take it as 10 to the power 5 pascals itself. This is also sufficient that we take it. All right. Next question arises is why fluids at rest exert force on the walls of the container as well as among themselves. So at 0 Kelvin, some have thermal energy. All right, some have already thermal energy with them. So they collide with them at a temperature greater than the 0 Kelvin. So basically kinetic energy of the molecules allow them to move, and that exerts force, which is and all the perpendicular forces, these are known as thrust. Rest of the forces are simple forces. So we say force per unit area is the pressure. So a similar quantity we have discussed in solids also. Stress. In solids, we had discussed the concept of stress, right? Then a small derivation we had done, which was the pressure exerted by the liquid column. This was the pressure exerted by the liquid column. That was H rho G. So H rho G is basically height of the liquid column. Rho is the density of the liquid. G is the acceleration due to gravity. This is H rho G. Now, then this pressure is called as gauge pressure. We'll be discussing this separately also because this is very important. And sometimes this is mixed with the absolute pressure. So it's just that you people should not be mixing this up. So we'll be discussing it separately also. Now, absolute pressure means if I'm adding the entire pressure, means the gauge pressure also I'm considering and the atmospheric pressure also I'm considering. So total pressure which I'm taking, this is known as the absolute pressure. So we practiced a question, and then lastly we had seen the concept of relative density. So relative density is basically the density of the body by the density of water. All right. So density of the body by density of water at 4 degrees Celsius. These two questions we had seen. Now we have to start with Pascal's law. See, Pascal's law is basically, Pascal's law says that, suppose, look at these points afterwards. First, look at this. Suppose I have taken a pipe, this much length is there of this pipe. And I have taken a very narrow pipe over here. And here also, I have taken the largest. And I have filled, suppose, this with water. This entire I have filled with water. They must be having their area. Let's say this is A, this is double the area, this is 3 times the area. Fine. Force will be exerted over here. This is the force. Suppose here the force is exerted. All right. Now see, if I talk about the first pressure over here, P1, here at this point, this is the first one. So P1 will be force per unit area. Fine. Now suppose I'm saying here the force that is being exerted is 2F. Come to second one. This is P2. This is 2F by 2A. So see, 2 will be cancelled, which is force per unit area. Third one. Suppose here the force that here that is being exerted is 3F. So P3 will be 3F by 3A. So this is equal to F by A. Now look, force upon area here, force upon area here, force upon area here. What can we conclude? P1 is equal to P2 is equal to P3. Why is it equal? This is, if you notice, this is equal at the same level only. This is what is Pascal's. Basically what happens, suppose this is a very narrow tube, area is very less, so force that is acting is very less. So here what will happen, in order to compensate and make the pressure remain the same, the force will double itself so that it narrows down to force per unit area. See, otherwise this would have been force divided by 2A if the force wouldn't have increased. So force doubles itself over here so that it reduces the pressure back to force per unit area. Similarly, here in the third case, the pressure becomes thrice, 3 times the force per unit area. So see, what is happening? The pressure is again becoming back to force per unit area. So why is this happening? This is happening so that the fluid doesn't come out. Suppose if I say from here the force is coming. So what will happen? If this force increases, so pressure will increase ultimately. If pressure at this second one increases, fluid which was static over here, if you look at, okay, this is the third one, I am not first, second, third. Okay, so yes, fluid which was static over here, now from first end and from third end, the fluid will flow out. So hydrostatics will be disturbed, hydrodynamics will be reached. So that's why in order to let the fluid remain at a point wherever the pressure is being exerted, it is transmitted equally in all the directions. If here the pressure was exerted, equal pressure was exerted here also. By compensation of force or area, that's a different thing. Whichever quantity has to increase or decrease, that's a separate thing. But the compensation occurs and the pressure remains the same. This is what is Pascal's law. Now come to the statements. This you can write it as note point also. An increase in pressure at one point of the enclosed liquid at rest. See, enclosed liquid at rest, pressure at one point, increase in pressure. Suppose the pressure increases over here. So pressure will be, force will be decreasing. So this will be transmitted equally in both of these. They'll be further compensating it to make it equal. So an increase in pressure at one point of the enclosed liquid at rest is transmitted equally to every part of the liquid and to the walls of the container, provided the effect of gravity is neglected. You're not talking about gravity. Gravity's effect is negligible in the sense whatever forces are coming, they are overcoming gravity. Gravity is not dominant over here. So that's why we ignore gravity. You will be seeing gravity in hydrodynamics also. You will be seeing in buoyant force also. Buoyancy we will be studying. There also you will see gravity. Now, what are all the note points which you have to keep in mind? Pressure in a fluid at rest is same at all points. This is a very important point which you have to remember. This is the basis for all the numericals. Now, Pascal's law of transmission of pressure. This basically says that a change in an incompressible fluid, this is transmitted equally, undiminished to every part of the fluid and walls of the vessels. Understood? The way to every part of the fluid and undiminished. That's why here the compensation occurred, and pressure exerted at any point in an enclosed liquid is transmitted equally in all the directions. When I say the pressure in the fluid is at rest is same at all the points. This means even if you modify the shape of container, suppose if I tell you this is one container, this is one container, and this is one container. See, Pascal's law basically says that suppose I have taken these many containers, 1, 2, and 3. All of them have different shapes, but the water level is same. So if I take this point and I take this point, then I take this point. So pressure at these points are same according to Pascal's law if they are at rest. Note down Pascal's law, then we'll discuss some more things. Yes, the height and volume should be same. Correct. Otherwise, if volume is larger, then how will the pressure be same? Then entire physics will change. P is equal to H rho G V rho. It's just that shape doesn't matter. Pascal's law is applied even if the shape differs. See, hydraulic lift, you people must have heard for vehicles, this is used, heavy vehicles, because we have to create lots of force. So this is based upon principle of Pascal's law. So if a question comes to explain the application of Pascal's law, best answer is hydraulic lift. All right. So here you will be using the entire concept of hydraulic Pascal pressures only, Pascal's law. So what did we understand in Pascal's law? Basically, the pressure which is unequal gets transmitted equally at least. So pressure remains the same. So in hydraulic lift, basically what happens? There is one narrow tube whose area is A1. I have already written this as A. This A is just a point to mark it. Area is A1. So here the force that is being applied at this end, this force is F1, or it force on the narrow end. Then this is the wider end. On this wider end, we have this area, A2 is there, fine, and a load is kept over here. Load, heavy load, like the heavy vehicles, which cannot be lifted easily, where you need lots of force. So the fluid is kept with it. This is not visible to you. You are just able to see this and this. This entire system is not visible, but this system is kept. Fine. Area is A2. Here some force will occur, that is F2. So what are we doing? We have created a very small, we have applied, not created, we have applied a very small force over here. That is F1. You can also see at this narrower end, the force is not very huge. So what is the pressure? Pressure is force upon area. P1 is equal to F1 by A1. Fine. This is applied over here. Now see, a very narrow force is applied, but what is the purpose? Even if the pressure here is F2 by A2, according to Pascal's law, P1 and P2 have to be the same because they are at the same level. Right, height of the liquid column is same. That's what I was saying to Harsha also. Height of liquid column is same. So pressure, according to Pascal's law, in order to maintain static flow of fluid, that is, the fluid shouldn't flow, what will happen? The pressure has to be the same. One quantity is fixed at one end, that pressure will be the same no matter what. So it means you have to modify the quantity, because you can also see without any modification, they cannot be equal. There is no comparison of this narrower end and this broader end, right? So what will happen? If the force that is applied is very less, area is also less, but pressure has to be the same. So here area is already more. The applied force F2, this will be very huge now. So what will happen? It will lift up the load. This is a huge force that is being applied, so that will lift up the load. So what is the benefit of doing all this? Benefit is that you have applied a very small force and a lot of force is being multiplied automatically. It's like if forces are same, so F1 by A1 is equal to F2 by A2. F2 is basically F1 by A1 into A2. So this increases itself. This is what is the concept of entire hydraulic lift. All right, this is already what has been written and what. Write it down, then we'll see questions based on Pascal's. Class, this question says in car lift, compressed air exerts force F1 on a small piston having a radius of 5 centimeters. This pressure is transmitted to a second piston of radius 15 centimeters. If mass of car to be lifted is 1350 kg, what is F1? What is the pressure necessary to accomplish this task? Fine. C, force 1. How would you calculate force? When we are talking, okay, forget force right now. First, let's talk about area because direct areas data is mentioned. So, small piston is there. So, area of cross section we will take. So, area of cross section will be pi r squares, 5 into 10 to the power minus 2 whole square. When we are talking about there is force 1 also occurring. When we are talking about force 2, second one, this is the mass given. So it will be mass into gravity, that is 1350 into 10, which is 1350 Newton, right? And what about area to 15 centimeter is the radius. So pi 15 into 10 to the power minus 2 whole square. Fine, this is the area force. So when we are talking about Pascal's law, F1 by A1 is equal to F2 by A2, right? So F1 will be equal to F2 by A2 into A1. You already have the data with you. F2 is 13500. A2 pi into 15 into 10 to the power minus 2 whole square into A1 pi 5 into 10 to the power minus 2 whole square. So it's basically like 25 divided by 125, right? 225, sorry. 25 divided by 225 into 13,500. This you can check and please let me know. This is the solution to it. Write it down. Yes, for pressure, you just divide force by area. F1 by A1 will give you P1. That is the formula of the pressure. So whichever side you want to find out, just divide that side's pressure by that side's area. Yes, class, this question answers. Nobody has sent this similar. At least first part, second part, you people can leave. Second part is just based upon hydrodynamics, one equation. You can leave the second part. First part, at least you people should have answered. Radii are also given to you. The two syringes, it says that two syringes of different areas of cross section filled with water. Basically, diameters are what? 1 centimeter, 3 centimeter, force is 10 Newton. This is what is of use to us rather than rest of the story. So let's not even write the entire story. What's of use to us? Basically, we know according to Pascal's law, F1 by A1 will be equal to F2 by A2, right? So F2 will be equal to F1 by A1 into A2. This is what we have. Now for area, we have no information about the radii. We have the information about the diameter. This is the diameter, no? Radius was given. I think, yes, diameters were given. So force 1 is 10 Newton. First area, d1 by 2 whole square by r square. Second one, pi d2. Sorry, I have interchanged, no? D1 and d2. This is d2, this is d1 whole square. So this is okay, 4 will also be cancelled, so only we are left with 10 into d2 square by d1 square. So this becomes 3 into 10 to the power minus 2 whole square divided by 1 into 10 to the power minus 2 whole square. So again, this whole square will also be divide. These will get cancelled. So 9 into 10 into 10 is also there, which is equal to 90 Newton. That's it. So this is the concept of hydraulic lift also, you can see. See, applied force was how much? It's like to one piston you are applying 10 Newton. On the other hand, on the other piston where the vehicle is kept, this tube, you are getting 90 Newton of force back. This is how hydraulic lift also works. Just write down this part. We'll just see a concept of gauge pressure separately. I told you, no? We'll see gauge pressure separately. Pascal's law is over. First, write this down.
Ma'am, what about the second part?
Yes, Harsha.
Ma'am, what about the second part of the question?
That is actually based upon one equation which we'll study in hydrodynamics. So that's why you can leave it for now. There's one equation of continuity that we'll see later. Okay, Harsha.
Okay.
Coming to, I hope you have written, no, the solution, all of you. See, gauge pressure, I have told you that basically the absolute pressure was the sum of the gauge pressure and the atmospheric pressure. So gauge pressure will be the difference between absolute pressure and the atmospheric pressure. That pressure is known as the gauge pressure. So for you, atmospheric pressure, for us, the atmospheric pressure is basically pressure exerted by atmosphere. That I have already discussed also. This value is 1.01 into 10 to the power 5 pascals. Now see, when I'm saying absolute pressure, when I'm saying absolute pressure, so it's the real pressure. It's the actual pressure. It's the actual pressure which is being exerted. Means total pressure at the free surface. This is the real pressure, actual pressure which is coming out. Gauge pressure is a selective pressure. That is just the pressure exerted by liquid column. Atmospheric pressure is a selective pressure. It's just the pressure exerted by the atmosphere. Total pressure, real pressure that is ultimately being exerted at the free surface of a liquid's end, this is known as the absolute pressure. This absolute pressure is the total pressure. So see these variables. Pg stands for gauge pressure, Pa or P naught, because mostly I use P naught also, and P stands for absolute pressure. So gauge pressure, when we are focusing on its absolute pressure minus atmospheric pressure, which is further taken just as H rho G. Also PA or P naught value, you should remember, this is 1.01 into 10 to the power 5 pascals. This value you should remember. I think I have mentioned also. I just wrote 10 to the power 5, write the entire. Okay, so net equation which used in the calculation part for total pressure, absolute pressure, is atmospheric pressure plus H rho G. We'll see questions, but first write down this theoretical part.